much for coming out to listen to my talk. I appreciate you all taking some time out of your day to be here. As he said, my name is Kelly Kirtland, and I am at Cornell currently. And I'm going to talk to you a little bit about outlier detection. And the reason I really got interested in outlier detection, well, probably the primary reason is because my advisor was really interested in outlier detection. But it actually became a very interesting topic in and of itself. I tend to be more of an applied statistician. I really enjoy dealing with data and actually getting into real problems that people have with real data. So outliers are one of those things that are becoming more and more of an issue, particularly in the age of big data, where people are not doing a very good job collecting random samples. You tend to have a lot of heterogeneous subsamples that don't necessarily fit. And people tend to just kind of take their data and run with it and assume it's all the same and keep going. Outlier detection is unfortunately a little bit ignored, I think, in the data age era when it's really become a lot more important that it happen. So I'm going to give you a brief overview of where we're going to go. Firstly, I'm going to describe to you a little bit what outliers are and why we go about detecting them, why it's important that we find them. I'm also going to give you a brief overview of some of the previous methods. There are many, but I'm going to go through the ones that tend to be most often utilized in the data today, and also describe to you the research method that I've developed in a very conceptual way. We won't be going a lot into the mathematics or the probabilistic implications of it. And then how to actually deal with the outliers once you find it. All right, so the general definition of an outlier was given by Grubbs, who had a very unfortunate name, back in a paper he wrote in 1960, which is essentially just an outlying observation is one that appears to deviate markedly from the sample in which it occurs, which is a very, very broad definition, which in English just means it's a point that's different from all of the other points around it. So for example, if you have a bunch of data points that fit very nicely together, but there's one that's just messing with things, it's saying everything you thought you knew is wrong, that point would be identified as an outlier. So we've hardly even begun this talk, and we've already gotten into a problem. The definition is itself not a very clear one. For example, if you look at this graph, most of the data points appear to be in one big blob off to your left. But say we have this one data point, which could exist at any one of these 6 locations. We could just take one data point and move it along this axis. Different analysts will disagree with you about where that data point actually becomes unusually far. Most people would probably say the first 2 locations are probably pretty normal. They don't look that far away from the rest of the data. And most people would say once you pull that data point all the way out to the end, that probably would be considered an outlier. It would be unusual. But somewhere in the middle here, it transitions from being a point that is a little bit different but not unusually different to a point that we want to say, yes, this data point is significantly unusual and we want to consider it on its own. Before we get in too much further, I'm going to give you just a broad overview of some vocabulary that will be important to you throughout this talk. And my students will probably have a good grasp on most of this. The first term is called a subject. A subject is essentially just one individual that you want to measure. So, for example, you might be interested in measuring a human being, like perhaps a student. Or if you're a biologist, you might be interested in studying trees. So a single tree would be a subject. And the sample is just the collection of subjects that you observe. You get a group of people that you're interested in studying, and you look at them all together. And then on each subject in your sample, you measure things that are called variables. Variables could be things such as height, GPA, or gender on students. They're all just specific attributes that we could evaluate on each subject. Or for trees, we might want to know about the number of rings. Like if you cut a tree in half, you can count the number of rings. We might want to know if it's a fruit tree, perhaps something about the yield, or the age of the tree. Now, there are many different ways that you can classify variables. The way I'm going to discuss variables today has to deal with the terms predictor and response. The word predictor just means you're taking a variable and you want to use it to explain the response variable. You might be familiar with these terms, independent and dependent variables. They essentially mean the same thing. However, in the particular topic where I'm going to focus, the particular methodology, predictor and response actually tends to be a little bit more common. So I'm going to stick with those for the purposes of this talk. So some examples of predictor and response variables. If we were studying trees, we know, if we go back to 3rd grade biology, we know that as trees get older, they have new growth, they get thicker, and as they get older, the number of rings increases. So we might want to use the age of the tree to predict the number of rings that the tree might show. Or for our students, they might be interested in knowing how much time they should study and how that's going to affect the grades they're going to get. They might believe that if they study more, they might get a better grade. Now, both of these particular examples tend to be sort of chronologically causative, right? Age is really what causes the new growth to occur with trees, and the rings kind of come secondarily. For students, the studying comes before they actually receive a grade. However, this is not necessary for the predictor and response relationship. For example, if you have a biologist who has a tree sitting in front of them, they might not actually know the age of the tree, but they can count the number of rings. So they might want to use the number of rings in order to predict the age of the tree, which is something they may not know. Or, as instructors, we don't actually get to see the amount of time that our students have been studying, but we do get to see their course grades. So we might want to use that information to predict how much time we think they have been studying. So usually, the predictor and response relationship goes in such a way where you take something that's fairly easy to measure and you want to predict something that might be a little bit harder to understand. I'm going to focus on the particular statistical analysis known as regression. There are lots of different types. Many of the most common statistical analyses are usually just particular instances. A lot of the issues you will encounter can really be grasped based on what we're going to talk about with regression. When you have regression, we put the predictor variable along the bottom, and our response variable is going to go along the vertical axis. Both of the variables we're dealing with should be numerical on a somewhat continuous basis. They don't need to be perfectly continuous, but they should be at least close enough to be reasonable. And each point represents a subject. So for in this instance, we have one student up there who seems to spend a fair bit of time studying and in return receives fairly good course grades. The purpose of regression is to obtain the line of best fit. Now, the line is a simplification of the data. It doesn't actually cover every single point that we see, but it does summarize it in a way that's fairly easy to understand. So a linear equation like this one, where we look at the expected grade based on the amount of time that a student has spent studying, involves a y-intercept, which in this case would just be the average grade we would expect for a student who spends exactly 0 hours studying. And the slope, b, stands for every extra hour that a student studies, they would expect on average to increase their course grade by that amount. All right, why do we even bother detecting outliers? For most of you, if you are data analysts at all, the reason you're probably here is because you have an analysis and you know that if there are outliers in there, then they're likely to cause you some trouble. And you want to find them so that your analysis will be a good one. However, there are also various fields where the outlier detection is actually the main point. Things like detecting credit card fraud. You want to find out the unusual observations so that you can flag it as being, this is not normal behavior. Someone may have been messing with this person's credit card, stealing identities. We want to just double check that this is actually that person. Things like perhaps the first day you get a credit card, buying a furnace and then driving across the country might be types of things that would be flagged as unusual behavior, which happened to my husband and I actually some years ago. It took about maybe 30 hours for them to shut down our card. So things like that might be very unusual. If you're interested in sports drafting, finding those particular people with very unusual attributes that might most benefit your team would be very interesting to know. Genetic sequencing. If you have two groups, what are the genetic codes that differentiate the two? So those are all types of things where actually detecting the outliers is the main point. But we're going to focus on the first, since that's probably why you're here. I imagine not many of you are into credit card fraud detection or sports drafting. So we're going to talk about really why they can cause issues. And really it depends. Depends both on the analysis you're trying to perform, and it depends on the attribute of the outlier. Outliers can affect things in different ways depending on where they exist. So if this was our starting point, right, this is the true model we actually want to know about. And then we add a point down here. Here we have a student who spends a pretty normal amount of time studying. They're certainly well within the range, but their grade is quite a bit lower than what we would naturally expect. This type of thing doesn't really affect the slope very much. And generally in regression, it's the slope that we're most interested in. So we usually determine influence in terms of how much it affects the slope. So here the slope is hardly affected. The only thing that happens is that we might say that we're going to underestimate the average grade of students who don't study at all based on this person. So this particular type of outlier is not terrible. It's not too bad in terms of actually creating a model. You might have a data point like this one, however. You have a student who studies vast amounts of time, but receives sort of a natural grade, something you would expect based on the general trend of the rest of the data. This particular type has a very unusual predictor value. It's a lot more time studying than we would expect based on the range of the other data. And this particular type is called a high leverage point. It's called leverage because any small fluctuation in the grade that this person receives is going to change the slope a lot more than any similar change for any other point would. So these are points where you really want to be careful. It could be really bad because any small change can really wreak havoc in your model. The third type are really the worst. They're the kinds that have very unusual predictor values. For example, a lot of time spent studying, and also do not follow the general trend of the data. They don't follow the line we would naturally expect to see. And these are called influential points, and they can drastically change the slope of your model. And in this case, it becomes either the model tells us that studying has no effect on grade at all, or that it might even decrease it a little bit, when in fact, for the majority of students, that's not the case. So that one point can entirely change our perception on how studying affects your grades. So we don't like those. Those are the ones you have to be most careful about. All right, how do you actually go about finding them? Well, the easiest way to find them is just to graph the data, right? We've been looking at graphs. They're fairly easy to see, and we like that. So if you can, we can just use our eyes. So for example, in this case, we have a young lady who is trying to convince a young man that she is, in fact, his significant other. So she presents this data, which is talking about the amount of time he spends. And all of the data points are between these two lines, except for her. She's way out here. He spends a lot more time with her than he does with anyone else, and so she makes the case that he is, in fact, her boyfriend. And her graph was so convincing that he agreed with her. So one variable works very nicely. Two variables also work very nicely. We can plot them very easily. 2 dimensions are things we're very good at seeing. We like to write things in 2 dimensions. And even if we get up into 3 dimensions, we can see things in 3 dimensions fairly easily, although this will depend a little bit on your computer software. Some software is not as good at visualizing things in 3 dimensions. But sometimes we have more dimensions than that. For example, if we want to make a prediction about weight loss, there are lots of things that go into weight loss. Firstly, the amount of weight that you start with. The amount of weight you lose tends to depend a little bit on how much you start with. People who weigh more at the beginning tend to lose more. People might be interested in knowing about the amount of carbs and protein and fat that people intake. What's the amount of exercise that they use? Was it aerobic or was it anaerobic? You know, all of these factors can go into this question, and we want to know about the effect of all of them together. And when we try and put that all together, we have a very high dimensional space, which is very hard for us to visualize. We're not very good at visualizing things in 20 dimensions. So graphing it, not always the easiest thing to do, because it's really limited to when you have, at most, really 3 variables, if your software is good. So that's not always good. The second option is create a model of your data. What do I mean by a model? Ian McGilchrist is somewhat of an outlier himself. He started out as an Oxford literary scholar and then decided to go into psychiatry and is a neuroimaging specialist at Johns Hopkins University. I don't know many people that go from English to neuroimaging, but he's one of those individuals. And he talks about a model as simply just a way of simplifying what we see. It's not going to accurately represent everything, but it's something that we can actually grasp hold of. It's something that we can understand. So we're going to use a model in order to try and understand the bigger picture. The model that you use is going to usually depend on your goal. So if your goal is regression, the model you compare your data to might be something like a regression line. We can also look at other things such as just the general distance of points to each other, or other options as well. But regression is a good one to start with. So when we create our model, we can then look at the distance of each point to the model. How far away is it from what we thought we should see? And any points that happen to be unusually far, in this case, our high residual point down here, our student who spent a pretty average amount of time studying but had a much lower grade than we thought, has a distance to the model that's maybe twice as far as any of the other points. So we would identify that point as being an outlier. And that's lovely. It works very nice. However, we have to be aware that when we're making models with data that could have outliers. And the whole point of looking for outliers is because they might affect our model in the first place. Nate Silver is probably the most famous statistician in popular media today. He is well known for doing a good job of predicting things like presidential outcomes and even sports games. And the reason he's been so successful is because he knows that when you're influencing the model you're using to predict something, that's going to change your prediction. And this is similar here. So it could work in instances like this, but when we have an influential model, when we've created our line based on all of our data together, our one influential point out here actually is closer to the line than a lot of our non-outlying points. So we wouldn't be able to identify it based on this model. It would look like a pretty normal point. So models don't always work because our models can be sensitive to outliers, which is why we're looking for them in the first place. So we have to be cautious of that. The third method that gets most commonly used are called influence measures. And what influence does is it essentially evaluates the amount of change in your model by including or excluding certain points. So we start out with a whole model, and then we can go through each individual point and see what effect that has on the model by leaving it out. And if the model doesn't change a whole lot, then we say, okay, well, it's probably a fine point. But when we get to a point like this one, when we leave it out, and we can see that the line has changed a whole lot, we would say, okay, this point is a problem. We went from having a negative slope to a positive slope. That's probably an influential point. We just left out one point, and it changed the model a whole lot. But we have another problem. What if there are 2 points that are outliers? Now, when we leave out that first point, we don't actually see a change in the model. So we would miss these points as well. All right, so influence measures, problematic, because if you have more than one outlier, which if you have any, you probably have more than one, it's not going to work very well. Also, if you have a lot of points, it can take a lot of time to go through all of the models for every different point that you're trying to create. There have been some new methods proposed. Most of them have not really gained any traction in the general statistical venue, the field. So the focus instead has been on what are called robust methods. These are methods that if you input data that has outliers, they just won't have as big of an effect. But outliers are actually really interesting points. Like, for example, if we had that student who spent a lot of time studying but got very poor grades, that's someone we want to know about. That's someone we want to be able to help. So trying to identify those points can actually give you more information than just simply trying to plug and chug out a model. So my solution, let's do some research. All right. My method is called the blocked adaptive computationally efficient outlier nominator algorithm. And since nobody wants to say that more than once in any talk, we gave it a nickname called the bacon algorithm. This is a particularly ironic name, bacon, because it was proposed by my advisor, who happens to be Jewish and doesn't eat pork of any sort. All right, the basic premise for this is that you start out with just a few points that you know are not outliers. This is actually a much trickier step than it sounds, because the whole problem is that we don't even know what points are outliers. So how do we pick the points that are not outliers in order to include them? So this one step has actually been the primary focus of my research up until now. My solution is to find 2 perpendicular lines, which are going to maximize the variation in the data. So we're going to look for the long parts of the data, right? And because we look for the long parts, it tends to follow outliers very well. And once you have those 2 lines, you look for large gaps. You look for unusually large gaps. And we're going to ignore those points that are beyond a large gap. And we're just going to pick points somewhere in the middle of what we have left over. And standard methods are usually pretty good for finding points in the middle if there aren't any outliers. Once we have those points, we can then build a model. We already know they're not outliers, so we can trust our model fairly well. And based on that model, we can add additional points that are pretty similar to that model. Once we have those new points, we can build a new model, and we can keep going until there are no more points that should reasonably be added to the model. Any points that are not found to be close to the model are identified then as outliers. Now, this particular method is actually quite good for a lot of reasons. It does very well for data sets that have a lot of outliers. Even up to 50% of the data can be considered as outliers, or in that case, you might consider them to be heterogeneous subsamples that you want to deal with separately. And this is a very useful thing when in big data you actually have a lot of non-random sampling. And non-random sampling tends to cause this to occur more often than true random sampling. All right, pros and cons of my model. Pros, it works very well for large numbers of variables. These are any number of variables up to about the number of samples that we have. I'm still working on how well it does when we actually have more variables than we have sample points, which is a very big question in today's data world. But it is very fast. It can be done usually within about a minute for about 10 to 100 million points, which is very quick, considering you have 10 to 100 million points. A lot of things just break, so that's a pro. Cons is that it does tend to flag non-outlying points as outliers something more often than traditional methods. The plus side is that it doesn't flag very many. It usually flags less than 1% of the data points that are available as being outlying. And it does a much better job of actually picking up on any outliers. The other ones don't flag non-outlying points very often, but they also don't pick up on the outliers themselves very often. You also can have occasional difficulty in the high residual points. Those are the ones that are pretty normal in the predictor variables, but are not common along the regression line. All right, the big question. Once I have the outliers, what do I do with them? If you have ever done data analysis, you have probably approached this question, and you have probably approached it this way. You found an outlier, and you're all excited because you did it. You did something that may have been very challenging to do, perhaps not so much in 2 dimensions, but maybe in 20. And then you just are left confused. What am I supposed to do with it? Rem Koolhaas, who actually is a very influential person. He was named as one of Time magazine's most influential people in 2008. And he's an urban design professor at Harvard University. He takes influence and he just says, I don't even want to think about it. The best thing that I think to do is just to ignore it, which is not really the best thing to do in statistics, because when you have influential points, you're going to get wrong results. So I'm going to give you some guidelines in what to do. The first thing to do is look and see if you have any errors. You might have a multinational kind of study going on, and if you're dealing with things cross-continentally, you might have variables measured in different units. For example, places in England tend to use meters, while we tend to use feet. You will get different results if you have values that are both listed as being in meters and in feet and mix them together. You want to have everything on the same unit. You also want to look for any just simple data entry errors. If you look for something that is actually impossible to have happened based on your system, that might be some kind of data entry error. You want to fix that and look into what happened there. Secondly, you probably want to check your distributional assumptions. Almost all of your data collection and analyses have some kind of distributional assumption. So you may have been using that distributional assumption and found some outliers, and then you just move ahead. But those points might be unusual in the distribution that you assumed, but not in the distribution you actually saw. So the best thing to do would be to double check and make sure that your distribution, both with and without those points, are reasonable. If you have a normal distribution assumption, as most of you probably would, things like the Shapiro-Wilks test or QQ plots would probably be the easiest way to go. The third thing to do would be try and determine why are the points unusual in the first place. What variables actually make them strange? This can be very interesting just to find out what's going on. You can get a lot of information from this. You also want to make sure that there aren't large groups of points that exhibit similar behavior to that, because then you might have a subgroup that you want to deal with separately. We did a common exercise with my students at Cornell, and what we'd do is we'd have them collect data on home mortgage prices from their hometowns. And students who came from the New York City area had very unusual values for their possible real estate prices, because really the real estate market in New York City is not really comparable to most of the rest of the world. So you kind of have to take the New York City people out and compare them on their own scale, and then it would work much better. The fourth thing is generate your model with and without the outliers and see what happens. If you put them in and then take them out and see that the model didn't change a whole lot, you're probably fine to leave them in. This is kind of similar to the influence measures, but you can do it very quickly, and you can do it with groups of outliers, so you don't have to deal with the one outlier problem. Fifthly, don't just assume that you have to remove them. Unusual things happen in real life. There are people who are unusually tall. There are people who are unusually short. There are going to be things that happen probabilistically that are unusual, and that's okay. It's reflecting real life, and taking them out might affect your understanding of real life and might make it slightly incorrect. So don't just assume that it has to happen. If it's not an error, if it's not impossible, you don't have to take it out. If you think that it's going to be influential, which you can judge based on question 4, there are robust methods that will deal with this. They will allow you to include the effect of these outlying points without allowing them to take over the whole thing. So don't just assume you have to remove them. And sixthly, and this is probably the most disappointing point of my whole talk for all of you, is that it's your data. You have to decide. You do what you want with your data. You're the one who knows it best. Take the information you know about how the data was collected, what's normal in these situations, and make the best decision that you possibly have. Just be honest. If you take points out, say so. If you left points in that are going to affect your model, say so. Let people know what the effect is going to be. But by all means, do not iterate this process. Don't go through and say, I'm going to take out these points, and then go through and say, hey, these points now look weird, and take them out. And then go through, oh, these points I didn't see before, those look weird, and take them out. Do not do that ever. But apart from that, once you've found some data points that you think are unusual, you can take them out or leave them in. Just be honest about it. I want to thank you all very much for your attention. Does anyone have any questions?